believe it? It's chapter 4. Did you know this exists? Yeah, it totally does. Yeah, I love Secret of Evermore so much. A friend of mine started replaying it, and I was like, oh, I haven't thought of this game in years. And now I'm just playing the music for you all, because it was like my first exposure to ambient music, I would say. Which I'm going to play a bunch of. It's going to be mostly just the jungle stuff during the first break, but... Alright, welcome back to 161. We're finally on chapter 4. So that does mean that quiz number 3 is going to be due this week. So quiz number 3 is due on Thursday, the 26th. Make sure that you turn that in by the closing date, which I believe is Friday. Alright, I'm a little congested. I think it's just the pollen. That's my best guess. Or it's cats, I don't know. So I apologize if I have to keep stopping to drink water or cough or whatever. Alright, chapter 4 is all about bonding. We're going to learn about ionic and covalent bonding. Excuse me. Some of this is review from Chem 140. You'll also notice that there's this weird little blurb at the bottom here. Now, my understanding is that when we first started teaching this class that they wanted us to do this. I still do it. So we are going to talk about chapter 10 real quick. This is part of something that you'll be tested on, but I'm going to wrap it into chapter 4. It's important for biology, but you may cover it again in 162. So it's just something that I've added to this course because it logically fits. Sorry, I had to cough there. Ugh. My throat is all scratchy. Alright, so let's go ahead and get started here. For the purposes of this class, we've basically just assumed that atoms were stuck together through some sort of force. And we've called those forces bonds. We're going to discover that there are actually multiple different types of bonds. We're going to define 2 of those types in 161 here. First, let's define the overall premise behind a bond. A bond is any interaction between 2 atoms that holds them together to form either a molecule or a formula unit. Now, we manipulate the electrons in various ways in order to get bonds. These, the manner in which we manipulate stuff is going to influence the outcome and the properties of the substance that we get. That being said, there are a lot of gray areas here. And so we're going to have to be very careful about how we describe stuff because there's a lot going on. And there is a Goldilocks sort of like just right in between those 2 extremes that we're going to talk about. The 2 extremes we're going to talk about are ionic bonds, which form between any 2 ions. So we sort of skipped over how to form ions in chapter 3 at the end there because in 140 you learned how to do that. You should know that you can make an ionic compound out of, say, sodium and chlorine and what its formula is, or magnesium and nitrogen and what its formula is, and so on. But once you've formed those ions, the nature of the ions is that they come together due to an attraction of electrostatics. Opposite charges, so positive and negative, will attract to each other. Like charges do repel each other and would not form a bond. So we have to have oppositely charged ions. Now, if we're using elements to do this, one of our elements must be a metal, which would be our cation, and the other must be a nonmetal. I guess we'll highlight this too, which would be the anion. Cations tend to form from metals because metals want to get rid of their valence electrons. The reason being, we talked about this very briefly in Chapter 3, if you have a full S&P subshell, you can make a stable ion. So removing valence electrons will do that. We're going to formalize that as the octet rule in this chapter. For anions, those form primarily from nonmetals. Because nonmetals are very close to having a full sp subshell, we just add extra electrons to that. It makes them both more stable, and then the result is that the ions attract to each other. Now, what is the physical nature of the object that we create when we make an ionic compound? It looks like this. This is a lattice. A lattice is a structure composed of alternating ions arranged in some sort of pattern. Sorry, I had to cough there. If I pause for like 5 seconds, it's because I'm coughing. I don't want to cough on the mic, so. Alright, here's our sodium chloride lattice. These are alternating charges, and this is actually the simplest arrangement, where each one has a charge of 1, either positive or negative here. If I had a positive 2 on, say, like magnesium, I would have half as many purples for the same number of chlorines. If I had, like, say, oxygen instead of sodium, I'd have half as many of these green ones substituted out for oxides, and so on and so forth. So the structure of this is only really unique to this sodium and chloride here. Oh my goodness, my throat's so scratchy. Sorry, I've been talking for 2 hours. I think it's catching up to me. Alright. Now, what's interesting about these ionic crystals? Well, when we form a lattice, the attraction between each of these ions is very, very strong. So this sodium right here is attracted to this chloride, this chloride, this chloride, this chloride, and also the ones in front and behind. So the amount of energy it takes to turn solid sodium chloride into, say, gaseous ions is tremendously high. In fact, we would have to heat this to roughly like 1,000 degrees. Is that Fahrenheit or Celsius? I never remember. So, melting, let's see here. Point NaCl. 1,474 degrees Fahrenheit, or 801 degrees Celsius. That's the melting point of sodium chloride. To get it to become a gaseous ion, or in other words, boil it, you have to heat it even hotter. Now, an important thing to note is that the lattice shown here is not a great representation of what the molecule, quote unquote, is for our ionic compound. We use the term formula unit to represent a particle of an ionic compound that can be repeatedly drawn. Now, I am simplifying here by circling just a positive and a negative. In reality, what we do to generate the repeatable unit is we actually like draw a cube, which would extend into the back of this lattice right here. And it's called the unit cell. And what the unit cell contains is the whole thing contains a bunch of parts of sodium atoms and chloride atoms. But when you add them all together, you get the same number of each. So, like, there might be each of the corners would have 1/8 of a sodium atom, but there's 8 corners, so that's 1 sodium atom. And then I'm cutting, like, chlorine atoms into half or whatever. But there's, like, 3 halves or whatever. And then there's so on and so forth. You end up getting the simplest repeatable copy and paste in a cube. Oh my goodness, I'm dying here. This is obnoxious. I hope I didn't catch COVID because I picked someone up from the airport. I'm going to be real upset. So I am simplifying by making this the formula unit for our purposes. In reality, it's a unit cell. But as far as we're concerned, the formula unit is just what represents the formula. So that's good enough for our purposes. All right. So that's ionic bonds. Ionic bonds, again, the formation of ions between two elements by transferring electrons. And then those ions are attracted to each other. Now, in covalent bonds and covalent compounds, we don't have any charges available. So we need to form bonds in a different manner. And the way that we do this is that instead of transferring electrons from one substance to another, we just have two atoms share electrons with each other. And they share them in a certain way. Now, almost universally, covalent bonds will form between nonmetals, but there are some exceptions. And we're going to explore some of those exceptions as we go through Chapter 4. All right. Now, how do bonds physically form? The answer is that when we want to form a covalent bond, I need to share electrons, but in order for me to be able to share those electrons have to encounter each other. What that means is that the electrons being inside orbitals need to overlap their space. Now, these two electrons can't be shared from this distance effectively. If I allow a little bit of overlap, then the electrons start to get closer to each other, and an attraction between the nucleus, which is the dot that I wrote there, and the electrons between it, starts to form. There is an ideal amount of overlap between the positive nuclei being at the center of these orbitals, and then this overlapped region where the two electrons are. That leads to an optimum. Excuse me. If I move these orbitals too close together, though, this is what happens. So if I have an orbital like, say, this, what I end up having here is that these two nuclei get too close to each other and want to repel. So if I had them at a distance of 0 apart, the repulsion would be extremely powerful. So there is some distance that is just right, where I have just enough orbital overlap for the electrons to be stuck between the two nuclei of the atoms, but the nuclei themselves aren't repelling so much that they push the two atoms apart. That ends up being the bond distance, whatever it ends up being. Now, the bond energy ends up being what amount of energy I need to put in to separate these two. In other words, if I was going to pull them apart, like if I could grab these with my fingers, like here's my finger and here's a thumb, or I don't know. Now it looks like a wrench. If I were to try and pull these apart, how much energy would I need to provide? I would have to provide this much energy to do that. We're going to talk about this in more detail in Chapter 5 when we draw pictures of orbitals and show overlap. But this is just a preview of what's actually going on. Now, in covalent compounds, all of the molecules are independent of one another, so it's hard to see in this diagram. Let me see if I can zoom in and that helps any. So each of these molecules is sort of stacked on top of others, but they're all oriented in different ways. So this hydrogen right here and attached to this oxygen is a separate molecule from the water in the background, hydrogen, oxygen, hydrogen. You can see that right here. This one is on top. It's completely separate from this other one that's right here. These are all separate from this. In fact, all of these molecules are independent of each other. None of them are bonded to each other in any way. Now, there are attractions that hold the molecules together. However, those are not bonds. And we're going to talk about what that means at the end of this chapter. That's what the intermolecular forces section is about. All right, so let's start exploring how to discover which type of bond occurs by introducing a new concept. So we don't talk about electronegativity in 140. We just say, hey, if it's a nonmetal bonding with a nonmetal, it's going to make a molecular compound. But if it's got a metal in it, it must be ionic. There is a little bit more nuance, and we're going to talk about that here. Now, if I have an atom pass its electron over, we would form an ionic bond. If I have an atom share its electrons with its neighbor, we would call that covalent. Now, could there be something in the middle here between these extremes? Is it possible for you to share something unequally? And the answer is, of course there is, right? If you're a kid and your kid sibling has the Nintendo Switch, like it stays in their room, you get to play with it, but it's in their room, right? So they get it whenever they want to, but you have to ask for it. And if they're playing with it in their room, you don't get to play with it. That would be an example of unequal sharing. It's more accessible to one person than the other. In atoms, that is absolutely possible. Electrons can be shared unequally. Depending on how strongly the electrons are attracted to the nucleus of one atom over another, we could have electron density be closer to one atom than another in a bond. And this leads to interesting behavior. So up above, I've drawn the Lewis structure of Cl2. We're going to do Lewis structures either today or Thursday. But if I had to say which chlorine is going to pull these electrons towards itself more strongly, you would say, oh, well, they're the same atom. So they're going to pull exactly the same strength, and the electrons should be right in the middle, and they totally are. So in other words, the amount of electron density across the chlorine-chlorine bond would be roughly the same throughout. You'd have the same probability of finding electrons closer to each side of the... let me try that again. The probability of finding electrons closer to one side over the other wouldn't be skewed towards one chlorine. It'd be the same probability, and you'd be most likely to find the probability of electrons in the center. But what if I do this? Who wants the electrons more, hydrogen or chlorine? The best way to think about this would be think about, okay, well, what forces are pulling on the electrons? So that would be Z effective, right? Chlorine has a higher Z effective. It's going to pull the electrons towards its nucleus more than hydrogen can. So what that means is that we're more likely to find the electrons over on this side than we are on this side. Now, they're still shared. Hydrogen is still interacting with chlorine in a covalent bond. But they're not shared equally. This will have consequences later on. Now, how do we determine which atoms will attract electrons to themselves more often? We use quantum mechanics to do that. Thankfully, somebody has already done all of those calculations for us, and that is this guy. This is Linus Pauling. Linus Pauling did several very important physical and chemical calculations to create this phenomenon called Pauling electronegativity. As a result, he went batshit insane. I'm not kidding. After he was done with his research, he literally went crazy. You can read all about that on Wikipedia. I just like this picture because it actually makes him look crazy. He's like, I'm surrounded by molecules all the time. But he was actually a very, very important physicist and chemist. And it is very unfortunate that what happened to him. I think he just too much going on. All right. We're going to define this property as electronegativity. Electronegativity is the ability to pull electrons towards the nucleus of an atom through a covalent bond. In other words, it's the strength of the atom at electron tug of war. Every atom has been ranked from 0 to 4 using Pauling electronegativity. The highest number is 4 on the periodic table. The lowest is actually like 0.7 or something like that. There are other electronegativity scales which are used in different ways. I believe P-table uses a different scale. But we're going to just stick with the Pauling scale because it's the most common. Now, very importantly, make sure that you do not mix up electronegativity with electron affinity. They are related, but they are different. The values for electron affinity have been incorporated into the calculation for electronegativity. So, electronegativity is not a mathematical formula. It is just a result. And those results look like this, sort of. Sort of meaning I don't have all the elements on here. But as you can see, the elements that go, or the elements increase in electronegativity going left to right. They also decrease in electronegativity going top to bottom. The highest electronegativity on the periodic table is fluorine. If you are in a bond with fluorine and you're playing electron tug of war, you lose. You cannot beat fluorine. Fluorine wants electrons the most. It is the smallest. It is the highest C effective. Electrons are just super attracted to the nucleus of fluorine. Atoms on the left side of the periodic table do not really want their electrons. They just give them up. All right. So whenever you're asked a question about electronegativity, I am going to be basing that off of this table. So use this chart for any electronegativity questions. If you use P-table or another source and the numbers are different, you might get an unexpected wrong answer. Okay, so just be mindful of this. Now, there is some interesting stuff that goes on in the middle of the periodic table right here. These are called the noble metals. And the noble metals have surprisingly high electronegativity. As a result, they have interesting chemistry. Or what I should say is they have more interesting resistance to chemistry. Gold, for instance, is almost as electronegative as carbon, which means that it's very, very hard to react gold with other things. Oxygen has a hard time taking the electrons from gold. As a result, gold can't be oxidized in the presence of oxygen. This leads us to end up with things like, say, gold rings or gold jewelry that remain untarnished. They don't tarnish easily. Silver has a much lower electronegativity, and it will tarnish in the presence of sulfur and make silver sulfide, which is like black and gross. And these other elements can and do tarnish a little bit, but nowhere near as much as, say, iron. You might notice that some of these elements are used in various ways. Like, for example, if you've ever had spark plugs that were like high-end, those tend to be like platinum tipped. And the reason that we use platinum is because it doesn't corrode as easily as, say, chromium or titanium or something like that. So this property, electronegativity, has very interesting consequences for all of the chemistry that we do. So we're going to refer back to these numbers quite a bit. So there's our trends on electronegativity. Electronegativity increases if you move up or right. It decreases as you move down or left. Excuse me. If you are curious on how to calculate electronegativity, you could look up some stuff online and see how it's done using the concepts of ionization energy, electron affinity, Z effective, N, quantum mechanics, etc. But really, what you see here on the summary page is this is good enough. Now, according to your chart here, we're going to use the numbers that we just had on here. And we're going to calculate the difference between the different atoms that are within our bond. Now, I'm going to make one change right here. I'm going to change this to a 5. And you'll see a reason for this. If I have very little difference in electronegativity between my atoms, then the bonding that we observe is covalent. In fact, it's purely covalent. The electron density in every bond is roughly in the center. Now, the reason that I put this to 0.5 is because a very common bond that is accepted to be nonpolar is this one. That's the CH bond. The difference in electronegativity between carbon and hydrogen is so small that it's basically pure covalent. So I'm increasing that difference to 0.5 because I don't think that the textbook is correct. I know it's a bold thing to say. We'll see if that strategy pays off. But for our purposes, we're going to consider C and H bonds nonpolar. And so I just want to make sure that falls in that range. Now, if I compare some other elements, so such as this, and again, I'm getting these numbers off the chart, which I have memorized for the common elements. When I look at those two elements, the difference between them is much larger. If I fall between 0.5 and 1.8, I call that polar. Finally, if I have a difference that falls larger than 1.8, we call that ionic. And you can find all sorts of combinations over here that would give you a difference greater than 1.8. Tons of them exist. Some of them will get you close to 1.8, and then it's just more like, okay, do we call this ionic or is it polar covalent? It's really going to fall into the realm of, well, it depends on what our experiment tells us. But here's our guidelines. So again, this should be 0.5. This should be 0.5. As you get closer to 1.8, this gets more nebulous. Where do ionic bonds actually start? It's hard to say, but we're just going to use these guidelines for now. All right. Now, when I take the number... Oop, I don't know what happened there. When I take my numbers and get the difference between them, what I can do is I can represent that difference graphically in some way. And so here's the first method that we can use. I know that the difference here is 1.9, but again, this is in the gray area. If I have a polar covalent bond, what I will do is I'll put a delta plus on the side where I have a lower electronegativity, and I'll put a delta minus on the side where I have a higher electronegativity, just to indicate that. And so that would be like, instead of having a molecule that had full charges, plus and minus, we would just use this to indicate, oh, there are partial charges. The other way that we can do this is we could say, okay, I'm going to put the plus next to the positive side, or less electronegative, and I'm going to point an arrow at the more negative side. So either of these methods is useful to us. We're going to use each of these methods later on in various capacities. The arrow method is going to be important for us for determining polarity of overall molecules. The delta plus, delta minus method is going to be important for us to just visualize, like, how do intermolecular forces occur. Oh, I just connect the positive side with another negative side, or whatever. So we're going to use both of them. All right. So what I want you to do is I want you to use whichever method you prefer, the delta plus, delta minus, or the arrow method, on any of the bonds here that are polar covalent. Now, if it's ionic, you're just going to put a solid plus or minus, right? So this would be for ionic. This would be for polar covalent. So, using the correct symbol, label all of these however you should label them based on their electronegativity. I put a little hyphen in here as a placeholder mark for whatever bond is supposed to be there. So that hyphen could be an ionic bond, it could be a covalent bond, it could be a polar covalent bond. But the objective here is to tell me what type of bond is there, and then, as an additional exercise, add the correct symbology. So I'm going to give you like 2 or 3 minutes to do that. I'm going to go refill my water because I've already drank it all. And we'll be right back to check up on you in just a bit. All right, one more minute, we'll go over the answers. All right, so let's rate these by electronegativity. So we'll first have to go over here and look at this chart. So sodium is 0.9 and chlorine is 3.0. Oops. There we go. Apparently I have more of these. So the difference in delta, or the difference in electronegativity would be 2.1, so this would be ionic. And so it would be appropriate to put those symbols there. What about for bromine and iodine? So if we go back over here. So bromine is 2.8, iodine is 2.5. So that would be that. This would be pure covalent, which I have been writing as nonpolar. And so there we go. That's all we write. Nitrogen's 3.0. I don't know what boron is. 2.0? Yeah, 2.0. This is polar covalent, so we would write something like this and that. All right. Any questions, let me know. We can now categorize bonds and tell if they are polar or nonpolar. All right, I've got more of these for you to try, but what I'm going to do is I'm going to let you take, we're going to take a break now. You can try these during the break if you want. I'll quickly go over the answers at the end of the break, so let's do this. I didn't clear this, so hold on. All right, so we'll turn the music back on. We'll take a 10-minute break, and we'll listen to some more Secret of Evermore. Alright. We are back. Let me turn this wind down here. Fun fact about The Secret of Evermore soundtrack. It was written by somebody as their first musical project as their foray into video game music. That person was Jeremy Soule, who eventually went on to write the soundtrack for a game that you might have heard of called Skyrim. Same guy. On the screen here, I'm just going to write these answers in real quick. So this is nonpolar covalent or pure covalent. This one's polar covalent. This is ionic. And this one's polar too. And so we can draw the correct symbology for each of these. So if they're polar, they're going to get something like, this. Or that. If they're ionic, we would actually put whole charges in here. So those would look something like that. All right. So now that we know how to do that with bonds, we're going to keep all of this in mind for later. This last slide is just about what happens if you have both polar and ionic bonds present. You can actually do this in polyatomic ionic compounds. So if I have ammonium chloride, this whole thing has a charge to it. So this would potentially form an ionic bond. But these bonds right here are all covalent because the electronegativity difference between nitrogen and hydrogen is about 0.9. So I have both covalent bonding and ionic bonding present in a NH4Cl. So it is possible for you to have both bond types present. Typically speaking, this is going to be with polyatomic ions. We're going to see this because polyatomic ions have covalent bonds in them, but the overall charge of the whole thing, it makes it an ion. So we'll see that later on when we talk about more and different types of bonding and we get to intermolecular forces. It comes up. It's not super prevalent, though. Yeah, that's all I got for that. So, the rest of the today is naming. Hey, remember naming? We spent a whole unit on that. Yeah, we got to do that again. Now, I'm going to operate on the assumption that you remember how to do nomenclature from 140 because it is very similar. I'm not going to skip it completely, but whereas I would probably spend like 2 or 3 hours doing nomenclature in 140, we're going to do this in 1 hour. So the goal is to have this section just done by the end of the period today. So here are the different categories of things that we will name. 2 of these categories are more or less the same, and that's these 2. So binary ionic compounds and polyatomic ionic compounds. We're going to name using ionic rules. We're going to name binary molecular compounds using covalent rules. And then acids follow their own rules. So these are highlighted in a manner to be consistent with what rule type you need. I might sneeze. Give me just a second. I thought I was going to sneeze, and I even did the but it didn't actually happen, so I might have to mute and sneeze in a second. But these are 3 different types of rules that we're going to apply. On the screen here, I have the algorithm for naming an ionic compound, so we highlighted that in yellow, so we'll just highlight that again in yellow. So whether it is binary ionic or polyatomic ionic, you're going to follow this scheme. You're going to name whatever the metal is. That's just the name off the periodic table. You're going to name the nonmetal with the suffix IDE at the end. So you're going to truncate out some letters. of whatever its normal name would be, and then append "ide." And we'll go over those names in just a bit. Naming the metal is pretty trivial. However, there are some exceptions to when we apply an extra little addendum to the name. So, if the metal is in group 1, group 2, or the metal is aluminum, all you need to apply is the name of the metal by itself. So that is literally just what you see off the periodic table. Any other metal on the periodic table needs Roman numerals to indicate its charge. So for instance, if I had this metal with this charge, so I have an ionic compound with a 3+ charge in there, I would call this whatever its name was off the periodic table. Then I would put a parentheses, and I'd write the Roman numeral for 3 after it. Very, very, very important. When you are typing names into Canvas, note the following. No capital letters except for Roman numerals. So you would capitalize the I's in the 3 for chromium-3, but you do not capitalize the first letter. Elements are not proper nouns. They are not capitalized. If you capitalize them in Canvas, Canvas will mark them wrong and you get no points. So be mindful of that. If you took me in my class in 140, you probably remember this. Or the Unit 12 test or Unit 9 test or whatever it was for naming. Marks everyone's answers wrong, and then I had to go back and fix that. Well, this time I'm giving you the warning up front. If you do this and it's marked wrong, I will say, well, remember, I warned you. You cannot capitalize element names. They're not proper nouns. The other thing to note is that there is no space between the end of the metal name and the parentheses for the charge. So there's no space here either. Don't input a space there. If you do, it will get marked wrong. Now, I'm not sure if your textbook actually lists the other elements that have fixed charges. Let me see if that comes up here. I don't see it. Okay. But some other elements are included in here, so your textbook may also include gallium, which is always +3, zinc or cadmium or silver. And I call this the stairway to silver because it's this little staircase that leads from aluminum down to silver. And these are all fixed charges too, but I never remember which textbooks have this. Some do, some don't. You are not required to know these, and for any of these problems, if they come up on your exam or your quiz, I've programmed it to accept either with a Roman numeral or without. Specifically for the elements that I've listed here, these elements for this right here, these do not have an element. So if you write aluminum 3, Canvas will mark it wrong. So just be mindful of that. I have updated Canvas to accept British spelling. So if you're using a different periodic table, you might notice it says aluminium. We don't add that extra I here in America, but the Brits do. I've accepted either of those answers on Canvas because I do sometimes input the British spelling for some elements myself. Sulfur, for example, you can spell with a PH instead of an F. I have it programmed to accept both of those because I don't know which spelling you have become accustomed to. So both are accepted. All right, that's how we name metals. Naming nonmetals requires stems, which are like the prefix of the element name. So like oxygen's prefix would be ox. Nitrogen's prefix would be nitra. And then we append "ide" to the end of it. So here's an example. Do I have the table of those? Unfortunately, I don't, and I don't see it in here. So what we'll do, we'll just quickly write them all in here. So let's just write all the ides in there. So we've got fluoride, we've got chloride, bromide, iodide, we've got oxide, got sulfide. Just in case you see it, we've got selenide, nitride, phosphide, and that's really it. Maybe if you run into arsenide, that exists, but nah, whatever. Those are the primary ones. So you can see that we've ripped off the ends of these names just to replace them with "ide." These names apply to negative ions only. For example, chloride right here is Cl minus. Chlorine is Cl with no charge. That's the neutral form. So be careful. It's very easy to forget this and then call something sodium chlorine and then it's marked wrong. All right, so there you go. That's how we name ionic compounds. Drop the name of the metal in the box, drop the nonmetal name in the other box. Make sure you put the "ide" on the nonmetal. So what would I call this? Well, this is potassium. This is bromine, but I replaced the end with "ide." And you get potassium bromide. So pretty straightforward. I'm just going to go straight to the example. Oh, this is important, though. If you have a formula that has multiple of something in there, you only write the name. You do not use numbers. No numeric prefixes. No mono, di, tri, tetra. That's for covalent. Don't do it here, okay? All right. Again, just as a short review, how do we put together ionic compounds? So this would be the formula that I'd get for this. How do I obtain this? Well, each cobalt is positive 2 charge. Each chloride has a -1. I would need 2 of each of this, 2 of the chloride to balance out the charge. So this would be total 2 minus, total 2 plus. When I combine those together, I get a total charge of 0. So that must be the formula. Hopefully you all remember how to do that. If you have any questions about making ionic compounds, let me know. We can go over it as a review. But what would I name this? Well, I have this ion right here, cobalt 2. So I'd write that. And then Cl is chloride. I misspelled it. Be very careful of misspellings. Canvas will mark anything wrong. There you go. All right, I'm going to skip the next example because I want to just put these on the board here. I want you to name these. I also want you to go in the opposite direction. Can you name, given a name, can you give the formula of that? So I'll give you 5 minutes to try these examples. I'll just number them real quick for you. And we'll go over the answers in just a bit. So see you soon. Let's do 2 more minutes and we'll go over the answers. All right, let's go over the answers here. So this one is lithium oxide. We got Be, which is beryllium. Chloride. Al is aluminum. And O is oxide. And then potassium. Iodide. All right. Next, we have these compounds. We need to give formulas for them. So the best way to do this, I find, is to write out the ion for each thing. So strontium would be Sr2+. Bromide would be Br-. We know which ions form because we want to have a full S and P subshell. And so now I can put these together. I need 2 negatives to balance out this 2+, so that would be SrBr2. Rubidium nitride. Here's my rubidium ion. Here's my nitride ion. So I put those together. I get Rb3N. Sodium sulfide. We got sodium Na+. Sulfide is S2-. Balance the charges. Magnesium and then iodide looks like that. Mgi2. Balance the charges. Put as many of each that you need to put down to balance out the charges. So here I need 2 total minus, so I just put a second one of these. That's where the 2 comes from. All right. Any questions, let me know. There is a page 2 of these. How much time do we have? Yeah, we could go ahead and do these. I'll give you 3 minutes to do these. We'll just number them 1 through 8 again. Or 1 through 7, I guess. So go ahead and do these, and we'll be right back. One more minute, we'll go over the answers. All right, let's go over the solutions. So, first let's name this. So this is cobalt-3 bromide. And then the formula would be COBr3, because I need 3 of the Br minus to balance out the 3 plus charge. This would be titanium 4 oxide. And it'd be TiO2 because I need 2 of these to balance out the positive 4 charge on that. This is chromium 2 sulfide. And the formula is CRS because I have the same charge on both, so they both just neutralize. CRS. Now, unfortunately, whenever I type stuff, PowerPoint auto-capitalizes the first letter, so these shouldn't be capitalized. They're capitalized because PowerPoint thinks that they are sentences, so just be mindful of that. So, what ions make this up? Well, here's gold 1, here's chloride, here's sodium, here's nitride, we got barium and oxide, and then platinum 4 looks like that, and fluoride is F minus. And if you wanted to combine these together to make formulas, you totally could. So gold 1 and chloride just go straight together because there's a charge of 1 on each. I need 3 sodiums to balance out this nitride, so that would be Na3N. Barium and oxygen already have each other balanced out. And I need 4 fluorides to balance out the plus 4 on platinum. All right, so that is ionic compounds. Polyatomic ions follow the exact same rules. All you need to do is drop the name of the polyatomic ion in the box. So if you had ammonium, you would just, instead of naming whatever metal you had, you would write ammonium. If, for example, you had, I don't know, chlorite, well, you don't name the nonmetal with "ide" anymore. You just drop this name in here. So follow the rules for elements just as before, but if you have a polyatomic ion in your compound, you just name the polyatomic ion based on that chart in Chapter 6 that I showed you, which feels like ages ago, and that's because it is. So, for instance, what would I call this? Well, the K part is the metal, so that would be potassium. And then MnO4 minus would be permanganate. Really, the hard part about this is going to be remembering what the polyatomic ions are or referencing that sheet every single time. That's something that you're going to have to work out on what is the best method for you. You can use that sheet on your quizzes or exams, so just have that bookmarked or have it printed out or do whatever you need to. And you'll be all set. So what would this be called then? Well, we got the metal. The metal is this part. And then what is this? This is hydrogen sulfite, because it's only SO3. SO4 would be sulfate. Or you could say bisulfate. Or, I'm sorry, bisulfite. Hydrogen sulfite and bisulfite are the same thing. Just a different term for the same compound. All right. So here are a bunch of polyatomic ions thrown in with some metals here and there. I think there's a second one of these. Yeah. Don't worry about the second page. It just has transition metals in there. So if you can do this, then you can do the second page, no problem. So I'll give you 3 or 4 more minutes to do these. Then we'll move on to covalent compounds. We'll do that real quick, and then we'll do acids, and we'll be all set. All right, 1 more minute, and we'll go over the answer. All right, so first one here, we've got NH4. That's ammonium. And then we've got sulfate. So there we go. I'm just writing out the ions so you can see them. We got potassium, chlorate. We've also got barium and carbonate. And then finally, we've got lithium and dichromate. There you go. And then these down here, sodium hydrogen carbonate. So there's sodium hydrogen carbonate, looks like that. We just put them together because the charges cancel. Ammonium nitrite. So we've got ammonium nitrite. We just put those together because the charges cancel. And then potassium and phosphate. These charges don't cancel, so I need 3 of the Ks to give me K3PO4. There you go. That's naming with polyatomic ionic compounds. Same general practice that we did before for naming all the rest of the ionic compounds. So we're all set there. Here are more examples. I'm going to just quickly write in these formulas for you in case you want these for your reference. Let's see here. Phosphate. There we go. So there's the answers to those if you'd like them. And again, any questions, let me know. Covalent compounds are very straightforward. The issue with covalent compounds is that you mix up the rules. This example is just saying to use parentheses for polyatomic ions. I'm not going to do any more of those examples. With molecular compounds, it's very easy to apply this rule to the ionic stuff. So what you need to do is you need to remember that numeric prefixes are covalent only. So remember that your first move whenever you're trying to name something should be to figure out, okay, what rules am I using? Is it ionic? Is it molecular? Is it an acid? What do I do? Once you've figured that out, then you know which algorithm to look up. So the boxes in the front here are just a numeric prefix that you're going to append to each element based on how many are in the formula. Now, what element goes first and what element goes second? You're going to arrange them by electronegativity. Simple as that. The element that is less electronegative is your first element. It's more positive, right? We've been putting metals first and nonmetals second because we're arranging them by charge. So we're going to keep doing that. If there is a tie, pick the element that's furthest to the left. So, for example, carbon and sulfur are very similar. You pick carbon first because it's furthest to the left. And again, numeric prefixes, covalent compounds only. What are the numeric prefixes? They're right here. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. These are all just past 5 or 5 and beyond. They're all just the names of shapes, right? Pentagon, hexagon, heptagon, etc. Mono, di, tri, tetra. You've heard of all these prefixes before. We're going to stick the correct prefix in front of the element name when there are that many of the elements. So if I had 2 nitrogens, I would write di-nitrogen. That would be something like that. And then some other part after it would be named whatever it is. So now there are some exceptions. If the first element only has 1, you don't write mono. For example, CO2 is carbon dioxide, not monocarbon dioxide. We got rid of that mono there. CO, for instance, which is going to show up in a second down here, looks like this, carbon monoxide. Which, interestingly, hits the second exception, or rule that we care about. If the end of your prefix ends in O or A, and the next word is oxygen, you're going to get this weird vowel combination. We get rid of the end of the prefix. So instead of having carbon monoxide, I guess, I don't know, like that, we get rid of the O on the prefix, and it becomes carbon monoxide. This is just a sound convention, I guess. This is what people have been doing because it sounded better. It removes a syllable from the extra letter. Just be aware of it. If you type it into Canvas and you don't remember to do this, it may mark your answer wrong. So be aware. And then again, no Roman numerals here. Roman numerals are only for metals that have charges that are variable. So there are no charges in covalent compounds, so we are not going to use any Roman numerals here at all. So what would you call this? Well, we just wrote the prefixes on the previous page, so we could say 2 is di, N is nitrogen, 5 is penta, but because I have oxygen, I would get rid of the A here and just write pentoxide. All right. What about SO2? What would I call this? Well, this is just 1 sulfur, but I don't put mono in front of the first element. But for 2 O's, I do include a di prefix, so I call it dioxide. And then finally, what would I call this? I mean, you might want to just say, well, it's water, right? Well, no, we can't do that. So this would be dihydrogen monoxide, also known as DHMO. I would do my little petition to ban dihydrogen monoxide joke, but we're short on time. I mean, it is on the next slide. These are all the things that water can do, and it's literally water. And my throat is too scratchy to do this. I need to drink more water here. Sorry, so you can read about these, you can laugh, like, haha, water does all these things. Yeah, if you breathe it, you will die. But yeah, the whole point of chemical nomenclature is that we have a systematic way to name things. Unfortunately, a side effect of that is all of the things sound chemically, and people are scared of that. Don't be scared of chemically sounding names, because they sound that way because they're systematic. If we just named every chemical like Hypnosil or Revivadrax or whatever, like, to me those sound scary because I don't know what the heck that means. Or Desiquin, or I don't know, Robitussin. Like, I don't know, these names don't mean anything to me. That sounds more terrifying than dihydrogen monoxide. So. All right, I'm going to give you 3 or 4 minutes to go over these answers. Unfortunately, that's going to be all the time that we have after we do that. So go ahead and do these covalent compounds. We'll name acids on Thursday. It'll be okay. One more minute, we'll go over the answers. All right. So we've got a 2 here for our nitrogen. That means this is dinitrogen monoxide, since there's one O. 2 chlorine, so that's dichlorine. 3 oxygens is trioxide. SF6, S is sulfur, no mono on the first element. 6 is hexa, and then fluoride. How can you get 6 of something around an atom? That's weird. How can you get 10 of something around an atom? What do we do with these? We're going to draw these Lewis structures later, so maybe not P4O10, but definitely SF6. P4O10 is tetraphosphorus. Deca oxide, but since AO, we'll just do dec oxide. There you go, there's that. All right, we've got diboron, so that would be B2. Trioxide is O3. Carbon disulfide, so carbon is just C. Disulfide is S2. And then oxygen O, difluoride F2. Covalent compounds are pretty straightforward. The real trick is don't mix these up with your ionic naming, because that's where all the problems happen. All right. We're going to do acids starting on Thursday, so we'll pick up here when we get to Thursday's lecture. I'm going to stop at this point today to try and just rest my voice and drink more water. So I apologize for ending 5 minutes early. But I do want to thank everybody for coming out to the lecture. Make sure that you ask me any questions you might have on Chapter 3 or Chapter 4 stuff, because we are almost to the end of the quarter, actually. The quiz for Chapter 3 is due on Thursday the 26th. So make sure that you get that done around then or by Friday. That's all I got. Have a wonderful rest of your day, and we'll see you on Thursday. Take care.